Good. So we start the second part, which concern the main topic of our lecture concerning this variably scaled discontinuous kernel. But first of all, let me show which is the outline of this part. The outline start introducing the variably scaled kernels. Then we say a few words about VSK and VSK interpolant. Then we move to the construction of the variably scaled discontinuous kernel. And we start by talking in one dimension just to understand the construction. Then we move to higher dimension. This is essentially the second part, which is the most important part of this lecture. So the main motivation, as we already observed, is connected to the shape parameter. Because the shape parameter, as we saw, is really a crucial computational issue when we use a radial basis function. There are many strategies to control or to tune this epsilon. In fact, we call generally tuning strategies. One of these is the so-called cross-validation that we have already seen, but there are other connected to the so-called contour pade, which is still a work in progress by my colleague Grady Wright and collaborators. Then I work on this stable basis because one thing that people coming mainly from a polynomial background is the idea of getting more stable basis for computations. And the point is that the only proposal in this direction is connecting to the so-called RBF-QR, the RBF-QR, which is mainly based on the use of the Gaussian function. So it uses the expansion of the Gaussian in a series of epsilon. This is one of the strategies. But there are some numerical results that we, because I'm one of the co-authors, we explored, and these are the so-called weekly SVD, weighted SVD basis. The weighted SVD bases are essentially bases obtained by using a SVD factorization of the collocation matrix, because every change of basis can be seen as the product of the pre-multiplication of a change of basis matrix. But there are then bases with different scales. There are some people that is working on a preconditioning the kernel matrix or the collocation matrix, as we wanted to call that. So in literature, you can find many options related to this crucial point, which is the so-called epsilon, the shape parameters. But there is our idea is to fix on this paper. In this paper that you have the reference in the bibliography that I put at the end of this lecture, is a paper by Bozzini and collaborator in EMA Journal of Numerical Analysis from 2015, where they introduced the so-called variably scaled kernels, which are based on a scaling function. So the idea is the problem that they solve is that finding the optimal shape parameter now is substituted by finding a suitable scaling functions which plays the role of a density functions. In some sense, the people, what they do is the following. So we look to the points and their distribution, so the points and the value of the points. And so we try to understand from this point if there is any scaling function that can be applied in order to describe better the behavior of the function itself. So the idea now of this variably scaled kernel is essentially given in this definition. So we start from this set which is actually a subset of the half positive line and a positive definite kernel. And then we construct on this subset of RD plus 1, so we are moving one dimension more. So this V is a positive definite kernel, in this RD plus 1. So given a scaling function, which is a scaling function, so is a function that take a point in omega, which is a subset of RD, and gives value in the positive real line 0 plus. So the VSK is nothing else than this kernel that we described in Formula 3. So essentially is the kernel phi, which is a subset in which the component in the d plus 1 dimension is obtained by the function, the scaling function psi. So in particular, we have a couple of observations that suppose that the kernel phi is radial, then the matrix, the collocation matrix, has components that can be described in this way. And in particular, you realize that when the psi is a function, when psi is simply a constant, which is the case when epsilon is chosen in the usual way, then you see that this part gone, and then you return to the classical collocation matrix. Well, there is this idea of the scaling function, and the idea of moving to the higher dimension in some sense is already explored in a machine learning setting, and it is called kernel trick. Probably people more expert than me in machine learning realize that indeed is this the case. So the two main references connected now to the work I'm presented from here onward are in these two papers. One is connected to a work by my colleague Rossini, in which she studied the VSK for gradient discontinuous functions. And this is the first paper in some sense that extended the or introduced the basis for the extension to the discontinuous case. Then we apply a strategy for the VSK partition of unity for solving elliptic PDEs in this paper in Journal of Scientific Computing 12 in 19. And then finally we set up all the idea concerning the variably scaled discontinuous kernel in this paper appear in BIT numerical analysis, numerical mathematics, in this year 2020. So we started to understand first what is the VSK interpolant. The VSK interpolant is essentially, as I said, so now we put this definition here, and then we define the new set of point in d plus 1 as, let's say, xk and psi of xk for every xk in x. X are our centers. Okay. Fix epsilon for the moment equal to 1, but can be any values, remember. So the interpolants, the so-called VSK interpolant, now take the form which is the following one. So we take a point, you see, psi of x, which is a point in RD plus 1 on omega, and then you compose this combination of values. So the point will be to find the coefficient in the usual way by imposing the interpolation conditions. So given the interpolant, we can project back on omega the points psi, big psi of x, and so the VSK interpolant that now we define as V sub f on omega is given in this way. So you have the kernel psi, phi of psi, Then we know that this is nothing else than the phi of c of x k, and so you see our VSK interpolant that we call Vf of x is nothing else than this Pf of psi of x. Okay. Now, what about the discontinuous? So we call variably scaled discontinuous kernel. The reference is the paper that I've already quoted in bit numerical mathematics. So we start in the one-dimensional case. So we learn from the one-dimensional case. So the idea is the following. Suppose we have a function with a discontinuity in a point xc. So in the point xc, your function on the left, the value is f1 of x, and on the right is f2 of x. But the function can be extended in the usual way, so using the so-called limit approach. So we can extend it to, we can make it continuous using the usual limit. Obviously, when we approximate function of this type, this originates the so-called Gibbs phenomenon, that is unpleasant ripple nearby the discontinuity. This is exactly what happens when you have a function with discontinuity. And so our solution to the problem was the following, is to consider VSK-like. We call at the beginning VSK-like interpolants. As in 4, so 4, remember, is of this form here. So the interpolant should be, in any case, a combination of something. But now we wanted to make more explicit what is this something. So the idea now is to consider a scaling function. So our psi now is a function that is alpha on the left of c of our discontinuity and beta on the right of c. Because you remember, I claimed that this scaling function has the property to mimic the behavior of the data. So you have a function with a jump in between. So the idea is to have this scaling function that in some sense describes the jump. And so that is the case for this function psi here. So this is a piecewise constant with a jump at the discontinuity point c as the function f has. So now we start, the idea now to the construction is the following. We start from a strictly positive definite kernel. I didn't say much about why we rely on this type of kernel, but there is a theory that says that every conditionally positive definite kernel can be reduced to a strictly positive definite one, and if you have a strictly positive definite one, you have all the property for existing uniqueness of the solution of the system, the linear system that comes when you solve the interpolation problem. So, going back to our construction, so the function psi is defined on omega times s. Now s is the set where we have the two values of our function. Now we are in the one-dimensional case, remember. Again, we take epsilon equal 1. Then we consider something of this form. So our phi composed with the two norm, because we are working with the radial kernel, reduced to this, and more explicitly using the explicit norm is x minus y to the square plus these values here. So what says the following? This says that our radial basis function psi composed with the psi is equal to the function phi of modulus x minus y when you are on the left of the discontinuity or on the right of the discontinuity. In between, you have these two values here, which is exactly the same in some sense because of the radiality due to the norm 2. So now we can construct the discontinuous, the VSDK interpolant in one dimension, which is nothing else the following. So we pick a set of point x. So this is a discontinuous linear combination. So our interpolant is a discontinuous linear combination of functions. Which are the functions? Well, these are the functions. So you see, if xk is between a and c, so is on the left of our discontinuity, so is defined in this way. If is on the right, is defined in the other way. And so the remark is that the v psi, so the interpolant v psi, is a linear combination of functions presenting a step discontinuity at the same point c. And so we can summarize all this idea in the following definition of VSDK in one dimension. So the definition is the following. Take omega, an open interval, then you take S is the set of value in some sense taken by the scaling function, and consider the set of the jumps. So it's a set of distinct points that we call the jumps that we assume ordered. So Cj is less than Cj plus 1. Then the scaling function will be defined the following way. So we do not need to have many values of in S, but simply we can get two values. One is alpha. You see when x is between a and c1, or x is between two jumps. Okay. Otherwise, the value is a beta. Moreover, what we want is the psi at the related to the interval CLB is alpha when L is even, or beta when L is odd. So we need this more information, otherwise something doesn't work. And so the corresponding kernel is called a VSD kernel on omega. And so again, we remark that this function having jumps in is a linear combination, interpolant is a linear combination of functions. So our function now, the radial basis function, or in some sense what we call the translates, having jumps at the same location as the function has, because we are trying to reconstruct function with discontinuity. So now the analysis cannot be done in the usual way. In the analysis of the convergence, because the idea is to understand if this VSDK approach converges to the classical one. And so what we do is here, this was the first idea, was to take a sequence of, let's say, scaling function. So these psi n are a sequence of scaling functions defined in the following way. As you see, n can be any positive integer. And so we reduce these, let's say, these values around the jumps with a limit construction, so that we have this one that at the limit when x tends to this Cj plus 1 over n, which is our jump, as n increases, tends, you see, to C2 of j, which is beta, and the same for alpha, for the other jump, the other values. And so, from the point-wise convergence point of view, we have that this series of scaling functions are converges to the function, scaling function psi of x, which is now defined using this limit process. So, for example, if you take two discontinuity here, one is in minus 0,5, one in 0,5, so you are in the interval, let's say minus 1, 1, but in minus 0,5 and 0,5 we have these two jumps. So we can define our series of functions converging to the scaling function, which is 1 on the left of C1 and 1 on the right of C2, and in between the values of this function, the scaling function is 2. This is a discontinuous function, as you see, but you can, using the limit process, to make it continuous. And so here I show you a picture which is quite interesting, because you have your function, the function that we are approximate as a jump here. You see in the point minus 0.5, 0.5, and is obtained like you see. There is an exponential negative, then there is in between the x cube, and then there is 1 on the right. Okay, so you see what happened on your function. Taking values, different values of n, because you see psi 10, psi 50, psi 500, and you see that it converges to the function psi, which is the one that we have defined before, 1 and 2. So taking these two values, we can reconstruct at a big value of n, but goes to minus 1, goes to the denominator, so it converges. So you get a perfect reconstruction of your function in the interval that we are considering. And here, what we use as a kernel is the matter kernel C6 with epsilon equal 1. Okay, and the set of points that we have taken were centered a grid of 80 equally spaced points in minus 1, 1. So we can do something more now that we know that this series of psi n converges to psi. We can ask to ourselves, but what's about the variably scaled discontinuous kernel obtained using this construction? Converges to the function psi? And the answer is yes, it converges, and in the paper that I quoted there is the proof about that. On the same line is also the interpolant, because the interpolant is defined as a linear combination. So as a linear combination we get as a corollary modulus all the assumption in the corollary. We have that in the limit with this construction we converges to the interpolant variably scaled based on the variably scaled discontinuous kernel. The same also for the power function. So we have the same for the power function, and so we can get this limit construction here, this estimate for the pointwise error in terms of the power function. Once we know that the power function converges in the limit, then we can describe the error, the pointwise error between the function at the variably scaled discontinuous kernel interpolant in terms of this power function and the usual norm in the native space, in this case of the psi, the phi of psi of this variably scaled kernel. The extension to the multivariate case is a little bit complicated, but was done in this recent paper in SciEM Journal of Scientific Computing. The idea for the extension rely in this three, let's say, main points. So that VSDK rely on a classical RBF, and therefore, in principle, it easily extendable to any dimension. This is a fact that RBF were studied exactly to avoid dimension of the problem. So that's why they are called dimension blind. Moreover, to introduce an interpolation spaces based on discontinuous basis function, we use a piecewise continuous scaling function. Okay, so for this space, we need a piecewise continuous scaling function. Then we associate to the kernel, the VSDK, a piecewise continuous. Then we associate, once we have constructed this, we associate the corresponding variably scaled discontinuous kernel. This is what we have done in this extension. So the assumption now generalize what we have seen in the one-dimensional case. What we have seen is that the bounded set is now a union of many subsets which are disjoint. Okay, so before we use interval, now we use subset. So we cover our domain omega with these coverings made by these sets which are disjoint. Then we assume the usual smoothness assumption of that the omega j satisfy an interior cone condition and have a Lipschitz boundary, but this is typical for everything that have to work. In RBF setting, you will see many of theorem that has this assumption. Then we take the jumps. So the jumps are in this, the jumps, actually, these are the value assumed by the scaling function. So the scaling function now is something defined in omega to this set C, or sorry, not C, is a sigma. This set sigma is such that phi x is equal to alpha I for all x in omega I. So in particular, psi is a piecewise constant on omega, and the discontinuity appear only at the boundary of the subset omega j. Moreover, we assume that alpha I is different from alpha j if alpha I is different from alpha j, in particular if they are neighboring sets. So we assume that we know where the discontinuity are, but we see in a moment, in a few minutes, that we are able to locate this discontinuity and using a kind of a machine learning strategy for doing that. So the definition now is essentially the same that we have seen in the one-dimensional case with the following. So we take a kernel now. So the construction now is using a kernel k in rd plus 1 times rd plus 1 that we assume strictly positive, definite, radial. And then we consider defined by a radial function phi. So our kernel is nothing else than this radial basis function phi composed as usual with the two nodes using the scaling function psi. So the kernel is well defined for all x and y. The discontinuity of the scaling function imply that also the kernel is only piecewise continuous. So we need to introduce what we have already called the native space. For the native spaces, we need two things actually. We start from the graph of this function psi. So the graph of this function phi is the set of the point x psi of x with x in omega, so it's a subset of omega times sigma. So the kernel defined on the graph, so on the Cartesian product of the two graphs, values of R, and the discontinuous kernel. So using this kernel and the discontinuous kernel K sub psi, we define the inner product space this, and the completion, which is actually the let's say the infinite dimensional space, and the second space is the one obtained by the translator. So the completion gives the so-called native space, respectively, of the graph and the, let's say, of the translates when y is in omega. So these are pre-Hilbert space, and then we complete, and then we get the native space corresponding to our discontinuous kernel. And so, first of all, we had to prove, in order to get the proper space, we have to prove that these native spaces are isometrically isomorphic, and this is what is proved in the paper that I quoted in SciM, Journal of Scientific Computing. And the reason is because the inner product space H, K of G, and H of K psi are isomorphic. This is the main reason. And so now we can associate a Sobolev space based on the decomposition of the domain described before, using the assumption 1 up to 3. So we define for an S greater than equal than 0 and P between 0, 1 and infinity the following space of piecewise smooth functions. So essentially, this space, you see that it depends on the two parameters S and P, is made by the set of functions such that if you restrict the function to omega I, it belongs to a Banach space. So is a Sobolev, actually is a Sobolev space, this one, for the subregion omega I. This is what are this set of piecewise smooth functions of omega. And so, assuming 1 up to 3, then we assume that the usual Fourier decay is typical. So this is an algebraic decay to infinity for S bigger than D minus 1 over 2, or 2S bigger than D minus 1, or 2S plus 1 bigger than D, as you want. And then what is the native space associated to the discontinuous kernel is nothing else than WPS2. So if you look here, we have SP, now is S2 here, with the norm of the two Hilbert space being equivalent, because if we prove that, and this is exactly what is proved in the paper that I quoted. So now we know that, and so we are able, and this is what you have proved also in that paper that I have referred, and then I invite the reader interested to look at. So we have this result about the error estimates. So the error estimate and H here represent the usual mesh size. So you see that there is a strict connection between the smoothness of the function and and H. So there is if the function has such smoothness, then you can include this in this exponential that appear here. So these are the three final remarks before going to the third part. So the theorems provide an explanation why VSDK interpolation with information of the discontinuity is superior to the RBF interpolation in the space, in the proper space. So we have to work in the proper Sobolev space of discontinuous function. In this space, the convergence of the interpolants depends only on the smoothness S of the function, as I have already claimed, in the interior of the segments omega I, and not at the discontinuity of the boundary. This is a very important point. If S is sufficiently large, the interpolation scheme prevents Gibbs artifacts in the interpolant, and this is exactly what we see later in the application. So we stop here for this second part, and the third part will be dedicated completely to the application and to some algorithmic issues.